So the hardest part in all of chapter 3 is probably chapter 3, section 1. That's the part that's going to take you the most time. So if you've done 3-1 and you're now just getting to 3-2 and you're a little panicked about your time for the week, depending on when you do this, you don't have to be very panicked. You might have to be a little panicked if it's Sunday night, but otherwise you should be just fine. The rest of the chapter talks about arithmetic. Now, this is why sometimes people who aren't going to be elementary majors, or even people who are, misunderstand this course. They see the description math for elementary teachers and they think to themselves, oh, that looks like an easy A. At some colleges, math for elementary teachers counts as a math credit. It's more often that it doesn't. One of the reasons that it doesn't is that to be successful in the course, you need a fairly solid math background. Um, you need something like math for liberal arts, or you need college algebra, something like that, or those similar skills to be successful in the course. And it is going to be simple as we talk about whole numbers and adding and subtracting and multiplying and dividing. But at the same time, it's going to be slightly more complex than you might think. And it's going to be more complex because we are not going to do this only the way that you've done it in the past. You're going to learn different ways to do these operations, and you have to do them in the different ways in the homework and on the exams and quizzes in order to get credit. So what we're going to talk about today, number relationships, including ordering and comparing numbers, different models of addition, the properties of addition, various addition algorithms, including but not only the standard algorithm, addition with number bases other than base 10. I'm going to talk about this. I don't think I've assigned any homework problems about it. However, again, this is the type of problem that often shows up. It might show up, I should say, on the Praxis exam for elementary. If in your future you're ever considering middle school, it will also likely show up on the Praxis for middle school math. However, addition in different bases probably wouldn't be more than a single problem. And then finally, some mental addition computational skills and estimation. So one way to represent addition of whole numbers, and we talk about whole numbers, the whole numbers are 0, 1, 2, 3, etc. So the natural numbers or the counting numbers are 1, 2, 3, and so on and so forth. The whole numbers add 0 to that. The set model is often how we inherently teach this in school, except we don't use set theory as such. But if Jane has 4 blocks in one pile and 3 in another, and she combines the piles, how many blocks are there altogether? This is a set model, and this is the type of problem we do all the time in kindergarten, first grade. Notice what we're really doing when we look at this as a set model, though. What we're doing is we're finding the cardinality of each set. This is why we talk about cardinality before we talk about arithmetic. We find the cardinality here of set A is 4. There are 4 unique elements in set A. We have 4 unique blocks. Set B, we have 3 elements. Its cardinality is 3. So the cardinality of A plus the cardinality of B is 4 plus 3 in this case, which is 7. This is the same as the cardinality of A union B. Now note here the sets have to be disjoint. They can't have elements in common, or we would get an incorrect conclusion. This is one of the issues that arose and one of the problems that people struggle with on the homework, and they struggle with in the set theories chapter in Math for Liberal Arts too. It's a problem like, this is the amount of people who like chocolate ice cream, this is the people who like vanilla ice cream, and these are the people who like both chocolate and vanilla. How many people like chocolate or vanilla would be this number plus this number minus this middle number, so you don't double count them, because these aren't disjoint sets. But these are. They're 2 separate sets. So there we have the official sort of set theory definition of it. And again, we don't teach set theory anymore in elementary school. Now, some of you are relatively young and you might have 30, 40, or longer careers as teachers. And how we teach math might change again over that time. There have been times when set theory has been very explicitly taught in elementary school. And there's been times, as probably when you went to school, certainly when I went to school, when it was not explicitly taught. Let me go back here a second, but this set theory model, even though we don't use set theory, is how we often tie addition to real world objects, whatever they may be. If you have 2 Unifix cubes and you are given 1 more, how many Unifix cubes do you have altogether? And we eventually learn to write that as our number sentence 2 plus 1 and to find the sum. But what we're working with there is a set model of disjoint finite sets. In other words, there's a countable number of things. The second major model that's used in elementary school, and this one is explicitly taught, is a number line model. Kenzo has 4 feet of red ribbon and 3 feet of white ribbon. How many feet of ribbon does he have altogether? Now, I'll be honest, I don't particularly like number line work for addition and multiplication and things like that. That's just me, though. Don't take my preferences here as anything worthwhile in this particular case. But we have a number line, pretend that's straight. And we'll start with 0 here. Of course, the number line goes on forever in both directions. We don't worry about negative numbers in elementary school, in early elementary school especially, although it's certainly possible, especially if you teach in a northern state where the temperature goes below 0. In something like a number line model, what we might see, and there's more than one way to do this, so read your textbook to look at how they do it specifically, but you might do something like, well, 4 feet of ribbon is here, and then 3 feet more, so I'm going to jump 3 to the right. 1 foot more, 2 feet more, 3 feet more. Oh, Kenzo has 7 feet. So a number line model can be very beneficial, and sometimes, in fact, students will even have number lines on their desks. We also use number lines when we order numbers, and they're very beneficial for that. And so a number line can help a student make this idea like a 2 is less than 4, or 6 is greater than 1. Students often have trouble with the inequality symbols, probably because we don't use them very much, because they look a lot alike. They're just flipped, and we know that students have problems sometimes flipping letters and other things. By the way, just because a student flips a letter does not automatically mean they have dyslexia or any other reading or other disability. Although letter flipping is certainly a symptom of dyslexia and other disabilities for some students, it's also developmentally normal as students are starting to appreciate letters and to understand that a letter is a letter even when it's at a different angle. And from that, you could see how it might be really easy for a student to think, well, isn't this also a B? Or isn't this also a B? All I'm doing is moving it around more. But I digress. But you might have the same reason for why we have trouble with less than and greater than. One thing to remember is that the point always will point towards the smaller number. All right, here's another one. One day, let me erase the ink on this slide. One day, Laura drank 4 ounces of orange juice in the morning and 3 ounces at lunchtime. If she drank no other orange juice that day, how many ounces of orange juice did she drink for the entire day? So both of these are number line models. Here's how your book would illustrate it. So not exactly the same as I did, but somewhat similar. From 0 to 4, and then 4, and we count 3 more. And then above it, we get 4 plus 3, and we see that that equals 7. When you draw a number line by hand, you want to be, if it's for an assignment for me, I completely understand if it's not precise, just like my drawing. It should be more precise than my drawing on the screen because it's hard to draw with a mouse for me. But on paper, you obviously don't need a ruler, but you could take something else to line it up or just use the lines of the paper. But you also want to make sure that the distances between the numbers are roughly equal. It doesn't have to be perfect. I'm not going to measure, but you don't want it to be like this. You don't want it to look like 1, 1, 2, 3. Those are roughly equal. Then all of a sudden you get 4, 5, 6, and then 7. So again, go for roughly. Obviously in the classroom, it's going to be more important to be much more equal than that. And so when you're drawing them on the board, or if you're presenting them on a computer, you'll make sure of that in a case like that, of course. All right. So in this case, students need to understand that the sum that is represented by any two directed arrows. We might call those a ray in geometry, an arrow that has just one arrowhead on it, can be found by placing the endpoint of the first arrow at 0 and then join it to the directed arrow for the second number. And there can't be gaps or overlaps. And we saw that on the screen. And then we can see what the sum of the number is. And we see that here. There's no gaps, there's no overlap. We go from 0 to 4, and then we start right at 4 to get to 7. So I already mentioned a little bit, these are the official definition of less than. You'll see the greater than in a minute. You don't need to worry about the official definition. There's also, of course, this other sign, which is the less than or equal to. And that can also be tricky for students. We don't use this as much in elementary school, although that depends on your curriculum. So A is less than or equal to B means either A is less than B or A is equal to B. It could be either of those things. So it would be a true statement to say that 2 is less than or equal to 2. Perfectly true. And then A is greater than B is obviously the same as B is less than A. In other words, we can switch the order of numbers in an inequality or variables in an inequality, but when we switch the position of the numbers or the variables, we have to switch the position of the number, of the inequality sign. One common strategy for adding is counting on. So this is a strategy that children are often taught. In this way, addition is performed by counting on from one of the numbers. So 5 plus 3 means you start at 5 and then you count 3 more from that. So we have 5 and then 6, 7, 8. 7 and 4, we start at 7 and we count 4 more, 8, 9, 10, and 11. It's a very common strategy that's taught. This is a strategy that before it was commonly taught, students would just sort of come up with on their own. And what we realized over the past 30 years is that some of those strategies that students come up with on their own are strategies that good, strong students come up with on their own, and that we can help other students by explicitly teaching them those strategies. You'll notice that so far what we haven't talked about is rote memorization. We haven't talked about knowing that 7 plus 4 is 11 because you've memorized that number fact. Instead, we've talked about strategies to figure out those number facts. We'll talk more about that idea in a few minutes. Another strategy is using doubles. Students pretty early get really good at doubling things. So they can learn that 3 plus 3 is 6, or that 5 plus 5 is 10, or even that 7 plus 7 is 14. Now this is probably going to happen a little bit later. This isn't necessarily first grade addition. But as students do more challenging addition problems, doubles might start showing up. And students can then, once they get strong with doubles, realize that something like 6 plus 7 is really the double of 6 and then one more. 5 plus 7 is the double of 5 plus 2 more. 12, a little harder one, 12 plus 13 is the double of 12 and one more. 12 plus 14 is the double of 12 and 2 more. And then another strategy is that of called making 10 and then adding any that are left over. So you might make 10 when you add 8 plus 6. So you use a 10 frame to make a 10, and you can Google 10 frames. There's probably a picture of them in your book. But a 10 frame is just what it sounds like. It's a frame with 10 spaces in it, a little bit like an array. And so sometimes 10 frames or things like 10 frames come with numbers already on them, and sometimes they don't. But it's just something like this, and say if I'm adding 8 plus 6, so I'm going to put in first my group of 8. Pretend those X's are things I'm putting in there. So there's my group of 8. And now I'm putting in 6 more. So there's 2 more. How many left over? I have 4 more left over, so my answer must be 14. Again, there's more than one way to use a 10 frame. Look at what your book says. When you take math methods, you very well might talk about other ways to use 10 frames as well. 10 frames have become much more popular in schools over the past 20 years or so. And you certainly might have used those yourselves in school. And then a property that we don't really teach, we don't teach, but that you should know as an educator is called the closure property of addition. And this is true not just of addition of whole numbers, it's true of addition of any real number. If A and B are both whole numbers, then A plus B is a unique whole number. So if you know that 22 is a whole number and 75 is a whole number, which they are, then 22 plus 75 is going to be a whole number, and it's going to be unique. That's the only answer you would get when you add those two numbers together. A property you probably learned in high school algebra or before is the commutative property of addition. You can show this using a number line. You could also show this using rods, such as Cuisenaire rods or other generic brands of rods. So you see using the number line, we have at the top 3 plus 5 equals 8. And at the bottom, we notice that 5 plus 3 also equals 8. Students don't need to know the language commutative property, unless your curriculum says they do. But when students realize that 3 plus 5 is the same as 5 plus 3, it very much increases, or rather decreases, their cognitive load. It makes addition much easier. This is also true for multiplication. One thing that students will struggle with, of course, is realizing that while order doesn't matter in addition, is that it does matter in subtraction. And then we have another property you're familiar with from algebra, most likely, the associative property, which means that we can group numbers together how we want. And that's why things like the doubling strategy work, because 10 plus 10, so 10 plus 10 plus 2 is the same as 10 plus 10 plus 2. So 2 10s and 2 more is also the same as 10 plus 12. So if we're adding 10 plus 12, this strategy helps. They're actually going the opposite order for that, rather, but same idea. The identity property, another property we don't explicitly teach, but that helps students and that students don't understand always at first, is that any number plus 0 equals that number. 0 is called the additive identity. You as a teacher need to be able to understand what properties go with examples, and you need to be able to give examples for all of the different properties. So make sure you pay attention to that in your classroom. Or, sorry, make sure you pay attention to that in your textbook as you read it. We talked about base 10 blocks in a separate video. This is something that you will need to work with a little bit in this book. You are going to be asked to draw using base 10 blocks at times. You do not need to put the little lines between each square like they do here and they do in your textbook. That is much more detail than you need. If you were drawing 14, you can do a very rough, long, and then rough squares for the units. If you're drawing a flat, you're drawing a large square. And if you're drawing the cube or the large cube, you're whatever you want to call it, you can just draw a large cube. You don't even need to put the dots in there, but something like that. So with our concrete model, what we're showing here is that 14 plus 23 is 37. And so this is the simple model that doesn't involve any regrouping. So a child just shows 14 with base 10 blocks, and then maybe their shoulder partner shows 23, and then they add their base 10 blocks together and they count and they see, oh, 14 plus 23 is 37. As you'll learn in math methods, a concrete approach should be introduced before the abstract approach. We should always start with concrete whenever possible in elementary math. So the standard addition algorithm, which you would do after you've exposed children to the concrete approach, the standard algorithm is shown on the right of your screen. This is a simple problem without any regrouping. But first we add the ones and then we add the tens. We work in the standard algorithm from left to right. This is hard for students for a variety of reasons, including the fact that since they've come to school, if not before, they've been taught that you read from left to right. But yet when we do math problems for addition or subtraction or for multiplication, in the standard algorithm, we do the opposite of what we've been training our eyes to do all the time when we read. And that's one of the reasons why that's one possible reason why a student might struggle with the standard algorithm. One way that can help students is to look at this as an expanded algorithm. This just makes some things a little clearer sometimes. So in 14 plus 23, first we add the ones and we put that on a line by itself. And then we add the tens. We add 10 plus 20 and we get 30. And then we add 30 and we bring down our sevens basically. We add 30 plus 7, we get 37. Here's an example of the extended algorithm with regrouping, which is when it really comes in handy. Students struggle with regrouping for a variety of reasons. Again, base 10 blocks can help with regrouping. You can't, some base 10 blocks actually let you break them apart now, I believe, but even if they don't, which I don't think they need to, you can still show students sort of trading in to regroup and remind them you can never have more than 10 of a single block before you need to regroup it, or whenever you get to 10 of a block, you need to regroup it or trade it. So here in our first row, we add our ones and we see that 7 plus 8 is 15. And in our second row, we add our tens. 30 plus 20 is 50. 15 plus 50 is 65. And then here's what you were likely taught in school, the standard algorithm with regrouping. Sometimes we use other terminology than regrouping. When I was in school, the phrase carrying was used, and I still slip and say that, but the word carry has no mathematical meaning. Regrouping does. Yeah, this is the standard algorithm. Now, this algorithm in education is always our goal. Our goal for our students is always for them to get to the standard algorithm, but we want them to get to it with understanding. And so that means we need to take time, particularly for some students, as we move towards that to make sure they understand what they're doing and why it works. So here's an example with base 10 blocks. We're adding 186 and 127. So you see the top row, excluding the dotted line part when the arrow, the top row here is showing us our 186. I believe that's 3, 6, 8, 86. And our bottom row showing us 127. So in our first step, what we do is we add the ones together. And with base 10 blocks, we sometimes will say, instead of regroup, we'll say trade, because trading does make a certain amount of sense with base 10 blocks. We aren't dealing with numbers there. We're dealing with concrete objects. And so we end up with 3 ones, and then we have one more 10 to join to our group. Then we add our tens together and regroup. So we have 8 tens from this number, 2 tens from this number, and 1 10 left from our regrouping. So we have 11 tens. We know if we get to 11 tens, we have to trade or regroup. So we have 1 10 3 ones, and then we've regrouped our tens. And so we've regrouped our tens into 100. So we now have 300. So we have 313. As I mentioned, students learn to read from left to right in English and most other European languages. And so it can be hard for students when they try to do math and it's the opposite direction. So there is a left to right algorithm for addition. This is the partial sums approach as well. And what we do here is rather than starting with the ones, we actually start with the hundreds. We start with whatever the first digit is. So 500 plus 700 is 1200. And then on the next row down, we go to our next place. 60 plus 50 is 110. And then finally, 8 plus 7 is 15. And then we simply add those rows. Again, these other algorithms and procedures are not quicker than the standard algorithm. And the standard algorithm in nearly every curriculum, I truly think every curriculum, is always intended to be where students get. By teaching these other algorithms, you are in no means prohibiting students from doing the standard algorithm. Rather, what you will do is you will help guide their learning along the way. And then one other alternate algorithm is called the lattice algorithm. And so in the lattice algorithm, we'll talk about this again for multiplication. Lattice multiplication is something that I personally really like. It makes multiplication easier for some students. It can even be used beyond multiplying whole numbers, and we can use it when we multiply expressions to an extent, at least in pre-algebra and algebra 1. Then there's also a lattice approach to addition, which isn't as commonly taught. Lattice multiplication is commonly taught. It's probably the most commonly taught alternate algorithm for multiplication. Your textbook was probably the first or second place, at least that I can remember, that I saw lattice arithmetic. It's a lattice addition. It's not commonly taught. But what it does is for each column, you put the answer right underneath it diagonally. So notice 3 plus 5 is 0, 8. And this is a thing that students will struggle with. They'll want to put 80 or 88 instead of 0, 8 here. 5 plus 6 is 11. 6 plus 7 is 13. 7 plus 8 is 15. So notice underneath what we do is we draw a box. We draw 4 boxes that are connected, and for each box we have a diagonal. Then we add on the diagonals. So 5, 1 plus 3 is 4, 1 plus 1 is 2, 1 plus 8 is 9. I personally think that some of the other alternate algorithms are better for addition than lattice addition. But although I used lattice multiplication in the classroom, I never used lattice addition in the classroom. So it might work very well for some students. So take what I say about that with a grain of salt, but it is something you as prospective teachers need to be able to do. There will be a problem about it in the homework. Column addition. In column addition, we add the numbers in each column and we write the sum directly beneath the column. Then we will regroup each place one column at a time. And again, this often goes with using base 10 blocks. There's examples of this in your textbook. In the opposite change algorithm, we decide which of the addends, remember addends are the numbers we add together in an addition problem, is closer to a nice number. And by a nice number, we mean a number that's really easy to work with, which is usually going to be 10 or a multiple of 10. And then we decide how to adjust that addend so that it ends in 1 or more zeros, and adjust the other addend the opposite way. So let's look at this as an example. Let's say I wanted to add without regrouping, that's a horrible writing. I wanted to add 88 plus 25. Here's how the opposite change works. Which of these is closer to a nice number? 88 is closer to 90 than 25 is to either 20 or 30. So Instead of 88, I'm going to add 90. How do I get from 88 to 90? I add 2. To make up for the 2 I added to 88, I have to take 2 away from 25. So now instead of 88 plus 25, I have 90 plus 23. And I can actually might break this down even more and say that's going to be 90 plus 20 plus 3. So 90 plus 20 is 110, plus 3 more is 113. So for the opposite change algorithm, we're looking for nice numbers. And that's always in the eye of the beholder. I could have done the other approach too. Let's say instead I said, well, I'm going to keep 88. I'm going to make this 30. So I add 5 to 25 to get to 30, which means I have to subtract 5 from 88 to get to 83. Or I could have subtracted 5 from 25 to get to 20. Then I have added 5 to 88 to get to 93. So the opposite change algorithm can also work. It's often something people will do when they're adding in their heads. And again, this is more for larger numbers. It's not as much for, 8 plus 7, although it works there too. I had 2 to 8, so I had to subtract 2 from 7. Another algorithm is the scratch algorithm. It's my second time making this part of the video, so let me erase my ink. So what we do here is we add the numbers in the units place starting at the top. We start with the units. And whenever we get to more than 10, or 10 or more, I should say, we scratch a line through the last digit added, and we write the number of units next to the scratch digit. So 7 plus 5 is 12. So we scratched out the 5 with just one line. We don't scribble it out. We just scratched it out. And we write the 2 next to it. Then we keep going. 2 plus 9 is 11, and we see the same thing occurs. So we scratch out the 9, we write a 1 next to it, and then we put in our number of units at the bottom. All right. Now we count how many scratches we've made. We've made in this column 2 scratches. So we write a 2 at the top of the next column because we've scratched out 2 values. Then we do the same thing. 2 plus 8 is 10, so I put my 0 here and scratch out the 8. 0 plus 6 is 6, that's fine. 6 plus 4 is 10, so I put a 0 here. I scratch out the 4. And since a 10 has 0 units in it, I write my 0 here. And then for this, I write how many scratches I had in this column. I had 2 scratches. So I have 201 as my answer. As you can probably tell from my stumbling, I never used the scratch algorithm a lot. It's not my favorite, but again, it's something that might work for some students. It's basically a way to make regrouping seem easier. And like anything, the more you do it, the faster you would get at. I'm not going to spend a lot of time on arithmetic and bases other than base 10. I didn't put any questions like that on your exam or your quiz, so you don't have to worry about that for our purposes in class. I don't think there's any homework questions either. But again, you might see it on a test in your future lives. And so one thing we could do here is use a base 5 addition table if we're working with base 5 rather than base 10. The other thing you could do is convert these numbers to base 10, add that, and then convert back your answer to base 5. And that might even be how I would do it. But what we can sort of see here is 4 plus 4. 4 plus 4 in base 5 is 13. So I'm going to write a 3 here. And remember, my answer is going to have a 5 in it as a subscript. And I'm going to carry the 1. 5 plus 3 is 8. So, well, sorry, we can't do 5 plus 3. I knew that. 1 plus 4 in base, can't even do 1 plus 4 in base 5, because 1 plus 4 in base 5 is 10, or 1, 0, I should say. So we'll do it this way. 3 plus 1 in base 5 is 4. 4 plus 4 in base 5 is, again, 1, 3. So we get 3 here, carry the 1, and 1 plus 1 in base 5 is blessedly 2. So we have 2, 3, 3, base 5. We could also think about this just sort of in our head, remembering we can never get to 5 in base 5. So 4 plus 4 in base 10, and fast forward this video until you see the slide change, because I'm going to babble a little bit about this and I don't want to confuse you, but if you're interested, keep listening. So we know that in base 10, 4 plus 4 is 8. And 8 is 3 more than 5. So this has to be 13. If I carry the 1, then again, I'm going to get 4 plus 4. That's going to be 13. Carry the 1, and then I get a 2. So we can think of whenever we see 2 plus 3 is 5, that's really 10. Whenever we see 3 plus 3, anything that would be 6 is really 11. Anything that's really 7 would be 12. Anything that's really, I say really, I mean in base 10. Anything that's really 8 would be 1, 3. Anything that's really 9 would be 1, 4. And then anything that's really 10 would be 2 5s. That would be 2, 0. Okay. Let's go back now to moving the slide so you can pay attention again. So we see how they do that. 2, 3, 3, base 5. Again, something to work on if potentially, but even on the, you will have to deal with other bases on the Praxis most likely, and you will have to deal with other bases in class, but addition, subtraction of them, things like that, unless you're going to be a math major, unless you're going to teach middle school math, you probably are not going to need to know that. Even if a question shows up on a Praxis about it, it wouldn't probably be more than a single question out of like 120 or whatever the elementary ed Praxis currently has on it. So mental math, adding, sometimes we like to add from the left. So if we take 76 plus 25, first we add the 10s, that's 90. Then we add the 1s, that's 11. And then we add those together. We could also break things up in bridge. So 76 plus 20 is 96. And then 96 plus 5 is 101. That also works. Or you could have done 25 plus 70 is 95. 95 plus 6 is 101. There's more than one right way to set these up. Trading off, we did something very similar to trading off before. We're working with nicer numbers. So we add to one number to make a multiple of a number of 10 usually. But you also might make a multiple of 25 or a multiple of 50 or a multiple of 100 depending where you are. So you might even say 76 plus 24 is 100. I would really want to add 100. Can I subtract 24 from 25 really easily in my head? Yes, I can. So 76 plus 25 is 100 plus 1. It's 101. Compatible numbers are numbers whose sums are easy to calculate mentally. This is what we do when we have, again, multiple numbers together in a list, like, 4 or more. So this list, what's really easy? Well, 130 plus 70 is 200. 50 plus 50 is 100. And so we get 200 plus 100 plus 20. That seems much easier to add than 130 plus 50 plus 70 plus 20 plus 50. And apparently what I said before was making a compatible number. All right. Other things of estimation, one is called front-end estimating. In a case like this, we just add the first digits. So here, 4 plus 5 plus 2 is 11. And these are all hundreds, so we have 1100. And then we make some adjustments. 22 plus 31 is about 50. 74 is about 70. 50 plus 70 is 120. So our adjusted estimate is 1100 plus 120. So if we were just adding the first number, that is front-end estimation. Adjusting takes into account really what our tens place is. Again, we can group things to nice numbers. 39 and 64, it's about 40 plus 60, that's about 100. 23 plus 32 is about 50, plus 49 is about another 50, so that's about 200. Sometimes numbers cluster around a common value, so everything here seems to cluster around 5,000. So we have 5 numbers that cluster around 5,000, so our answer is probably pretty close to 25,000. And of course, rounding. And depending, we might round to the nearest 1,000, or we could round to the nearest 100. It just depends. And then one thing with rounding is that I know that we teach rules of rounding, and I've talked about this in my rounding video, but those rules are really guidelines. They don't apply in every situation, and sometimes students don't realize that until they take statistics in high school or college. But in reality, there are times we always want to round up, and there are times we always want to round down. In budgeting, for example, we might always want to round down of how much money we have in the bank so we don't get overdrawn. Or we might always want to round up of what we're budgeting. Like my cell phone bill is around $93 a month, I think. And when I budget, I would typically round that to $100. That way, if they all of a sudden add a surcharge or the tax rate changes or something else, I'll still be within my budget. So there are times when you want to round up, there are times when you want to round down. And so here, if we have 7262 plus 3806, we first take a low estimate by taking just the first digit, 7,000 plus 3,000. And then we take a high estimate by rounding both up, and that violates the normal rules of rounding. Why do we do that? Well, here we do it because we know our answer is somewhere between these two values. And we might even get even closer and say our answer then is going to be around 11,000. That's accurate here, but it wouldn't always be accurate. But there are times when you want to say my answer is going to be in the range of 10 to 12,000. I know it's going to be more than 10,000, and I know it's going to be less than 12,000, but it's going to be in that range. All of these estimation techniques are ways to do math in your head, and they're also ways to check work. Not necessarily to check work to make sure you got the precise answer, but to check work to see that your answer is reasonable. So a whole bunch about addition in this video. I hope this proves helpful. I know some of the algorithms are a little tricky. There are practice ones in your book. Please do those. Please do assessment A as you need to. You will have to do most of these algorithms in the homework. If you have any questions, please let me know.